All right, we are nearing the end. In this lesson, we're going to talk about the potential for galvanic cells if we're under non-standard conditions, and we're going to relate cell potentials, equilibrium constants, and reaction quotients and use them to calculate one from the other. Okay, so this is where we left off on a previous slide, namely the relationship between the standard cell potential, E degree sign, E standard, and the standard Gibbs free energy change for the reaction that is actually driving it. But, so typically we're talking about species that are in solution. Standard conditions means that the solutes are at a concentration of 1 molar. And even if you start at everything being 1 molar, as soon as the reaction occurs by any infinitesimal amount, those concentrations are no longer relevant. So the standard cell potential is something that you observe, only for a fleeting moment. Same thing goes for the standard Gibbs free energy change. And we've, from the previous chapter, we did determine that the free energy change for a particular process actually does depend on the system composition. So the question is, how do you relate, let's say a standard cell potential and the standard Gibbs free energy change to the cell potential and the expected Gibbs free energy change for non-standard values. And the solution actually looks a lot like it did for free energy changes. So you may recall from a previous chapter that the expression that told us what the non-standard free energy change for a process is equal to its standard free energy change plus this factor R times T times the natural log of Q. This is the ideal gas law in the joules per mole per Kelvin, the absolute temperature, and this is the reaction quotient, which is where you enter in the instantaneous and presumably non-standard concentrations. And the expression for the cell potentials is exactly the same, and because of this relationship between free energy and cell potential, applies for standard and non-standard conditions. So the quantity negative NFE, here where E is the cell potential under non-standard conditions, is equal to the quantity negative NFE standard plus RT ln of Q. And expressed thusly, this is just a rearrangement of this product N times F. Standard cell potential, non-standard cell potential, equals the standard cell potential minus RT over NF times the natural log of Q. And let's not forget that the F is the Faraday constant, which is the charge of a mole of electrons, and N is the number of electrons or the number of moles of electrons transferred in the process. And this is referred to as the Nernst equation. And again, the appropriate value of R here is the 8.314 joules per mole per Kelvin value. And the other thing I'll tell you is to, when you're punching this into your calculator, be careful that you, in this case, that you use the natural log and not the base 10, because they are not the same. You often see this as a base 10 log, but there's then a factor of 2.303 that you have to put in there. So just make sure you use whichever one is appropriate. All right, so we have related cell potential with free energy change. We also related free energy changes with equilibrium constants and reaction quotients. So now the next logical step is to relate cell potentials with equilibrium constants as well. So we started off here with the Nernst equation that tells you that the non-standard cell potential equals the standard cell potential minus RT over NF times the natural log of Q. Now you may recall from an earlier slide that the cell potential is related to the equilibrium constant thusly. So it's equal to RT over NF times the natural log of the equilibrium constant K. So if we substitute this expression into our into our standard cell potential term here, we get this. The non-standard cell potential is equal to negative RT over NF natural log of K, or positive, minus RT over NF natural log of Q. And if you are at equilibrium, at this point, this is going to be equal to 0. So, once the equilibrium composition is achieved, Q is equal to K, these terms become the same, and the cell potential drops to 0. And at that point, any further progress stops. You're, at our chemical, we're at the lowest part of the valley as far as the chemical potential is concerned. So the moral of this story is that at that point the reaction ceases, and also the potential goes down to 0 as well. So no reaction, no juice. All right, so let's go through an example real quick of this. So this is going to be a two-part example that will get us to the non-standard conditions as well. But first, so I'm going to tell you that we've got two half cells. One is nickel, nickel 2 plus, and the other one is cadmium, cadmium 2 plus, are assembled into a battery like we've been talking about before. I have given you the standard reduction potentials for those systems. So the first question is, what is the reaction occurring in the cell? So hit pause, think about it for a second. Okay, and if you look at the standard reduction potentials, again, it's the most positive one that stays as the reduction, which is this one, even though it's a negative number. Negative 0.25 is more positive than negative 0.4. This one stays the same. This one gets reversed, which means that the overall reaction in the cell is nickel 2 plus reacting with cadmium metal, becoming nickel metal and cadmium 2 plus ions. And the next question is, what is the standard potential of that cell? And again, just to add up the potentials, this one remained the reduction potential. And this one remained this one became the oxidation potential. The sum is the standard cell potential is the sum of the two. So the reduction potential is negative 0.25 volts. The oxidation potential is now positive 0.4 volts because we flipped it, which gives us a positive 0.15 volts. Okay. Now let's talk about what would happen if you ran this battery with non-standard nickel and cadmium concentrations. And now we get to the third part of the question, which deals with the non-standard conditions. So the proposition here is that we're going to reduce the cadmium concentration to 1/100th molar and leave the nickel concentration at 1 molar. So what's the new potential going to be? And do you expect the reaction to be still the one that is written here, or is it going to switch its direction of spontaneity? Will it be the reverse reaction? So let's try to get a qualitative guess at the answer first. So from, let's say, using like the Chatelier standpoint, we are reducing the amount of, or the concentration of the products. So maybe you might expect that you want to replenish that, which would mean that you would further drive it in the forward direction. And if the driving force to go forward is increased, you might also expect the cell potential to go up a little bit as well. Now let's see if the math bears that out. So the relationship to exploit here is the Nernst equation. The pen here. Okay. Go for the dark red. And so the Nernst equation tells us that the standard cell potential under any generic conditions is equal to the standard cell potential minus RT over NF times the natural log of Q. And in this case, that's going to be equal to the standard cell potential, which we have determined from the previous slide. And excuse me, erase that here, it's going to be minus. This, by the way, is probably one of the biggest non-chemistry goofs I see, namely missing this subtraction sign here, and then RT and F, and then the reaction quotient is just going to be the cadmium concentration divided by the nickel concentration. And don't forget that because the metals are pure solids, they don't show up in the reaction quotient. And so here we can actually plug in some numbers. So the cell potential is going to be equal to the standard cell potential, which we determined was a positive 0.15 volts, minus, and the R is going to be the 8.314 joules per mole per Kelvin. Temperature, I didn't explicitly say it. When that's the case, you can assume that it's going to be 298 Kelvin. And remember the N, in this case, you can kind of tell that these go from +2 to a neutral. So this is a 2-electron process, so we're looking to transfer 2 moles of electron per mole of reaction, and then find the Faraday constant, which is going to be 96,500 joules per volt per mole. And those are the more useful units in this case of the Faraday constant. And that's going to be times the natural log of the cadmium concentration, which we said was going to be 0.01 molar at this point, divided by the nickel concentration, which is 1 molar. And if you work that all the way through, you get a cell potential of positive 0.21 volts, which means that in this case, it's going in the same direction, but actually has a higher voltage. And this is, again, pretty much the example of a non-standard cell potential. Now, let's take this one step further.